So good evening. Let's start this class. In previous classes, we were discussing about graphs, catalysts, and kind of carbon chemistry, metal carbon chemistry. So we will continue that discussion. So the first question that here you can see that among them they want to know the correct ligand for graphs generation, second generation catalyst. So it's very well known. So this kind of uh, ligand, NAC ligand, uh, is used for this second generation catalyst. So you can expect this kind of scaffold uh, with uh, there as ligand. So here that L2 here you can uh, write this kind of uh, carbene with five-member ring with nitrogen and their aromatic system is there. So, this is your L2. Now for L1, so for generation 2, actually, uh, this cyclohexenes they are used, not PPH3 little. So, there L1 would be this particular phosphorus base. So, this is the full structure of your graphs second generation catalyst. Now, if we look at the option, so they are actually generation one and earlier this kind of things are used. Now, as they specifically mention second generation, so that's why three option where this and this is there. That should be your op- now coming to the next question. There they asked about acyclic metathesis polymerization reaction. So ADMET, ADMET. uh, So acyclic diene metathesis. So they actually known as ADMET, this kind of polymerization. Now, if we look into the options that they have given, so for this first type, this is actually here you can see this ring opening reaction because so you can write ROM because ring opening metastasis is happening followed by polymerization. So for this case, they do the mechanism they need to be uh, more clear. So this is the double bond that would react fast. So let's say we have this kind of metalloadenine, metallocarbene. At first, this thing would be happening. So we would form this kind of intermediate. Now ring opening would happen. So the ring opening, you can see you have now generated this kind of thing. Now this portion can actually do the polymerization. So if you have a cyclic small olefin like say this kind of unit, now it can react with your this uh, tip center. So if you react over here, here we can have now this kind of uh, thing followed by normal cross metathesis. So that would lead to formation of this kind of diene in two helix and two fuse five members. Now these two units from here you can expect that your polymer can grow. Polymerization now can happen in this root center. So in that way you can understand this but first reaction mechanism goes via your ring opening polymerization. Ring opening metathesis followed by polymerization. Now for this case, so this one would be your acyclic diene metathesis. But we just saw the example of that because these two center with metal carbon can react and obviously these two paths can so that is called your AGMET. So the option would be C. So if we try to look into this mechanism, we can press that. So for this kind of cases, so as alkynes, so they also can react with this kind of metal carbons and do metathesis reaction. So let me clean the so, for alkynes, so they also behave quite similarly as alkenes. So now it can react with your uh, uh, metallocarbon. In that way, the same way the alkyne would. So for this case, you would generate this kind of like, now followed by this thing that would lead to formation of flame. This thing would happen. It would lead to the ring closure. and ultimately this is feeling followed by this lead to this closing kind of writing. So in that way you can explain this that spring closing is happening in that way and that's why it could be called as spring closing method. This part is meaning maintaining the for this, so this is normal cross method because R1 R2 they are actually interchanging like cross method will happen. So when it comes in that way, this two segment would be disconnected and followed by uh, uh, this part would react with the cell kinase and then in that is how that cross metastasis happens. So this mechanism is for cross metastasis. So if, they want to know that the DME. So that's why option B should be your option. Now coming to this, so they want to know the right monomer for making this kind of scaffold. So uh, look into it one by one. So with the first step given option, if we start the mechanism, um, so let's do that so that we can verify the option. So this is your monomer and here your wrap catalyst would react like this now followed by being opening. So we now leave formation of this kind of uh, thing prepared. We have that this kind of system. Now here generally this kind of small things are given and people they can react with this ultimately you would be having this kind of So here to choose five members are like this, and here actually your this part is there. Here two double bonds. Now from here actually your uh, this this can work and these two parts can grow to form this tree. Now, if you want to correlate with this polymer that you have given, so here you can see here we have only one double bond. But that for the first monomer A, we are having there are two double bonds, like you say, diins actually. So, this is not right. So, this is something where one double bond will be missing, which is the next. But here you can see that in this particular monomer, this double bond is not there. So, for if we do the same reaction, the same path will be followed, and we're going to generate this kind of. So, these two alkene units are not participating in this particular reaction, so their fate will be they would be unaffected. So only this particular area. So it be actually this kind of polymer can be formed, and that is nothing but that level of the given product which is matched. In that way, we can say that this particular monomer be the right choice for this polymerization reaction to make kind of another option. So here that five-member ring is missing, so your polymer would be in this kind of way if you use this thing, and for the option you would be having this kind of so different option, but here this particular double bond only would be possible if you use only this B mono. So that's how you can solve this one. Mm. So this from actually previous class. So this one is from a previous class. So there they have asked this ring opening metathesis polymerization, and we want to know among this kind of monomer units which would be suitable for or we should be undergo faster actually listening opening. So for first option, uh, propylene. So this is not a ring. So this is a cycling molecule. So there is no option of ring opening. So this is discarded. For now, we need to compare between these three options. So between cyclo, pentene, cyclo, octene. So, actually can be explained by your ring chain. And this not a born actually this kind of so here you can see the angle strain is much more for cycloentine compared to your cyclooctene or this kind of system. So according to that you can explain it because as it is a strain system that a particular ring tries to get much more stabilized with um, ring opening metastasis. That's why that this kind of five members like propane, this kind of ring breaking or ring opening would be much more feasible compared to your eight member or this uh, six member this kind of system. So that's why that five member is preferred compared to your eight or six members. That's why we use that correct. For stock metal carbene complex, and you know that correct statement regarding this. So, this kind of carbene is triplet and electrophilic, metal center is nucleophilic. Uh, so here metal center is actually electrophilic because that high oxidation state kind of metal are used. From platinum, this kind of high metal they are having that high oxidations. So that kind of things are used and they are stimulate and here it is nucleophilic because carbon if the metal is comparatively positively charged, so carbon would be this, so it is really nucleophilic in nature. So that's why D would be the option. So let's actually discuss a bit about that metallocarbene. So kind of often we can easily address. So let's discuss regarding this kind of carbene chemistry. So for regular carbenes, if you have this kind of units, so they have actually lifetime nanos because they are very much unstable or very much reactive. So most of the feature carbons are air and water stable, and in dilute acid or bases they are fixed. And despite of this high dipolar moments between the metal and carbon, they can be actually purified by normal Schlegel chromatography. So with this you can understand this kind of metal carbons are very much stable. So they are actually having this kind of distinct color uh, for different systems. Here you can see some of them. So those with sp3 carbons usually are yellow. So here uh, you can see that carbene it is attached to your LCH3 group. So it is a sp3 carbon. So for this kind of example, they are actually yellowish. And for sp2 means aromatic system or any double bond system. That kind of moiety is present here. They are kind of red in color. Uh, and for sp means this triple bond if it is there, it is black. So with the color itself, we can distinct between this sp3, sp2 or sp carbon, and the related carbon. So that's kind of visual uh, identification for this kind of case. Now, for rock carbon, so that was named after Richard Armstrong. So it is a nucleophilic carbon. So carbon, what we are just talking regarding that proposition, the options actually. Hmm. And carbon atoms need the triplets for swap carbon. So here it is a triplet, but it's not carbon center. It's not electrophilic. It is nucleophilic. So that's why it is not the correct. And again, metal is electrophilic and not. That's why this is wrong. So that's why this element is not. Now, coming back to this, so now for swap carbons, so your carbon is singlet state. So this kind of thing is there. So kind of dipolar interaction will be there because is the singlet. So charge distribution is there. And for swap carbon, it is actually swap carbon is triplet. So this kind of thing is there. And for swap carbons, so metals like high oxidation number, they are used. Early transition metals like titanium and tantalum, this kind of thing. And their ligands are non-pi acceptor ligands, non-pi donor ligands. But uh, uh, for actually fixer carbene, there you can see that the ligands are actually pi acceptor, pi donor property is there for fixer carbene. But for soft carbon, normal CH3, this kind of units are there where no hydration properties. So these are the some example of your short carbon. So here tantalum, titanium. So this kind of metals are used with having kind of +4 +5 oxidation state. So this is actually example of isolation of fast transition metal carbon complex. So that was actually isolated. So with this tungsten as carbon monoxide with methyl lithium, when it is reacted, you end up with this kind of moiety, and when it is reacted with your diazomethane, it ends up with formation of this kind of so here it is poemi and so it's nothing but this kind of thing. So kind of thing is first observed, and it's the actual example of fast transition metal carbon complex. Now, not only with tungsten, with chromium, iron, manganese, or cobalt, all with available all transition state transition metals, so you can have kind of methyl carbon molecule. And this one we have discussed. So, for singlet carbons, kind of high donation property is there. So complete donation of this happens. So that's why it is field empty. Just it's kind of interaction and so pi donation and pi acceptance. This property is there for Fisher carbons and they are singlet, singlet carbon. And for triplet or swap carbons, here you can see it is your metal and your carbon. This kind of interaction is there. So it's like a single bond property is there compared to your Fisher carbons and this kind of interaction. So here there is no kind of pi acceptance or donation property, only this kind of interaction is. So for your third type carbene, which is nucleophilic, that's your metal center. and for carbon it is uh, electrophilic. So that's how the what different environment is to metal, and that's how you can differentiate between them. So this thing will just first is this, and because and that's how your carbons can react with metal carbon can react with your electrophile or neutrophils depending upon its nature if it is soft carbon or it is a metal carbon. So if it can react with your electrophile, so here you can see this kind of uh, thing. So like this H minus would be by the electrophile, and for this it is acidic. So nucleophile can take this and this kind of stabilize. So there is upon that nature of your metal, these two property can be so this is a fissile carbon. So here your carbon center is electrophile. So nucleophile file like primary amine can react with this kind of substrate. So this can react like this and will be negatively charged or like this kind of OMe or methanol removal from this system will lead to formation of this kind of product. So it is this, for the sorprentanum is there, so highly positive plus 5 oxidation state. So uh, here plus 2 plus 2 and plus 5. So it reacts with electrophile. The dissolved acid, so electrophilic properties there. So here your carbon center is nucleophilic. So kind of attack with there and end up with formation of this kind of hydroxide. So that's how the reactivity would be different for your filter or short carbon. This is the general route for synthesis of this kind of these are carbon complexes. But was this kind of metal carbonyls are taken. With chromium, molybdenum, tungsten, this kind of metal can be used, and with lithium or maybe upon your hard good, this kind of lithium-based reagents are used at first, so that first nucleophilic attack is done like this. So here, this kind of thing, it's a Mikhail, or this thing would be happening. It should. to formation of this and here metal with obvious that stabilization and you have this kind of thing and followed by electrophile you can use to make it uh, OR in share can be varied depending upon your then carbon, they are nucleophilic, so we need these amines or uh, thiols, they can be used. So in that way, at first then this work they can eliminate and something would happen for sulfur. This should lead to formation of this kind of complex. This is the general approaches actually for fiscal carbons. So there are actually most direct and general approaches for making this fiscal complex, and the limitations are using this organic organolithium compound alkylating agent. So, this is another approach for this kind of fiscal carbons. So here kind of salts are used so that O minus and this tertiary methyl ammonium kind of dipeptide first form followed by a electrophile carbonyl so O minus will be reactor so AC kind of thing deforming followed by alcohol according to your choice that you want to incorporate over here you can do this kind of chemistry also. Now for this approach C18 with this thing is used. So for here at first, one carbonyl is eliminated and this kind of thing is there. Now it is a minus. So it is a nucleophile click now. So that's why this kind of six chlorides, uh, depending upon your R1, can be chosen and can end up with formation of this kind of carbonyl. So this will be as over here and followed by kind of same chemistry. So we can think of this kind of thing. Now the stabilization is there, metal carbon bond leads to this. Now after that, in the same way, that R2 can be used. And where if you want to incorporate amines, so that directly can be done. Uh, so from here to here, previously we have to let's say this kind of uh, amines if it is used then you can also get this kind of molecule but from here directly if you use this particular compound you can end up with this one. So this thing complete yeah. So these are the addition of nucleophiles so primary amine so in that way it reacts and this elimination with this kind of compound. So not only your amine, so this kind of vitiating agent also can be used. Now for that, for this case, let's see what is happening. So first, this center here over here and this elimination formation of this kind of unit. Here now we have uh, one, two, one, one, two, and we jump here. Uh, now same, I think, so kind of micro addition type, one for addition, we can say this, and followed by that, again, stabilization. So that would end up with here it is a six-member ring now, like this, and here this ring one is position, carbon is present here. So the phenyl is here actually. And this change to phenyl is here. Uh, in that if this particular part is react to, let's say, let's see, okay, if this happens now. Yeah, position. So now it is a six-member ring. One, two, three, four, five, six. And here you can see this kind of way. This relationship is now maintained. So at first, in lithium, this part would at first react, but not yet. This thing. For this kind of unit, amine would be reacting on this thing. See what happens. Hmm. Nitrogen would be here. So this only. This thing. It is nothing but a carbene. So this reaction would be to formation of uh, this kind of intermediate. So, yum. Mm, Now you have opening kind of thing now. Do the again in the same way it would be opening and end up with this vinyl and pH. So this kind of thing would be happening. Now these are that system. So now for this kind of carbon unit, so if you take this, so the pK values of this particular hydrogen are much more, because they are much more acidic in nature compared to normal carbonyl units. So that's one thing. And for this kind of intermediate with butyl lithium at first, and then this thing. So here, with this nitrogen can actually react with this particular substrate. Uh, now it in which, so at first with in butyl lithium, one of the protons can be taken up and have this thing. Now after that, what we react with your litho unit, and that actually leads to formation of this center. And after that, with this particular reagent, that carbon here, it is converted to. Initially, it is like this kind of unit. Now, after hydrolyzing it with this, you can have this kind of uh, beta hydroxy. How? you can say that, yeah, aldol reaction type product you can. So with this, we can kind of finish the show. Maybe the charge can be generated and you make it page the cell profile. It kind of ring opening lead to formation of a happy activity. Here or here it is we did, and this when uh, uh, kind of ring opening would lead to formation of this kind of product. Here it is. They are only reacted, so that's why this that's what first carry oxide like this. So this particular bond is now it can convert it to this. So one, two, three, four, five. Now this will be as about here is the elimination and internal cyclization of this kind of unit. So the another example is transfer of metal carbons to metal carbine into iron. So with the kind of carbene you use kind of Lewis acid like boron based Lewis acid at first it's kind of adapt to be there and followed by that alkaline unit incorporation liquid this kind of thing. So it is actually from carbenes to carbine this transformation. So for this particular reaction to benzanylation uh, dot say reaction at first if we have this carbene with carbonyl can have this kind of intermediate now it is we have to do it it's kind of alkynes so chromium and sort of high acid pi donation type interaction would be there to form this intermediate or adapt. Now, here you can see uh, can be reacted like this. So this large unit is replaced. Uh, yeah, right. Here, so let me now eliminate it. This kind of shift occurs. So AME is eliminated, and here you have now this particular bond. Yeah, I think, uh, this shift occurs in the small where that are this relatively smaller. This kind of shift intensity. So that's why you have now large and here chromium and here you have this kind of unit. This kind of shift happens, so minimizing the interaction. Now then again, from here. Now that your chromium based thing it is set towards this particular fifth position, and here you have carbonyl. So carbene type it is now present. And followed by again this cyclization lead to kind of benzene thing. Uh, Here this would be happening so that you can get aromatization and ultimately you have this kind of product. So this particular reaction is suitable for chromium molybdenum furan formation occasionally or this furan formation, and here tungsten is not also compatible. And for substitution pattern, so aryl carbenes with various substituents and naphthyls kind of things. So mm, some of the reactions with carbenes. So let's look into the mechanism. So you have this kind of unit. First is you have to this the, uh, now for this kind of that formation kind of thing, so you end up with the framing and see. So this is nothing but this particular part. Now here you have again that chromium. So again this cyclization can occur. Uh, so it lead to formation of uh, four member ring. So now you have this 5 and 4 um, unit. Here. Now with that we have now this particular kind of scaffold. Now just here I think one carbonyl beams are fit uh, there so that you have these 4 members and you would end up with this with the kind of field. So this is one and another is the kind of the incorporation between these two. Now what is they actually follow this kind of mechanism and you can end up with kind of so here the chain length is longer, so that's why you have ended up with kind of in closing necessity. It is 5 and 7 uh, according to that chain length. For this kind of effect, uh, again, it obviously going to react over here and so at first you have this kind of unit. So, here, no, this and here, any kind of this and this actually this carbon unit is reacting so that's how your this product is there. So you see here this position and this position is reacting with this. So that's why you have this 5 member type molecule. For metal carbons in catalytic carbon transfer reaction, where chromium tungsten they can be swapped by kind of heavy metals also, palladium, copper, and kind of thing. So they are actually very much reactive and unstable. So here you can see one of the example for that. So if palladium 2 and this carbon, at first this transfer happened and then only it reacted with this particular Michael acceptor and ultimately ended up with kind of uh, those circles. So that's all regarding this carbon chemistry, with metal carbon mainly. Now coming back to our questions to what we were solving. So now, with ring opening metathesis, they want to know the incorrect statement. So, their polymerization is non-living, it's a living because can growth happen. So, it is incorrect. So, incorrect, they want to know. So, it would be the option. So, cyclobutene polymerizes easily then nor bonding system because obviously for a cyclobutene you have very much higher ring strain as this 90 degree almost. So ring strain or angle strain is huge. So ring opening would be much facile in that kind of system where you have the one is fixed one. So it's a correct statement. The molecular weight distribution of is generally narrow. Again, this is a right statement and block is possible. So this is now coming to this. So this kind of equilibrium. So it is known as one-slit equilibrium. So if if you hit this kind of scaffold, at first you are going to generate uh, generate this chloroform would be removed and this carbon is generated. Now it can be actually in equilibrium like this or dimer kind of formation and this is called as this acyclic equilibrium. The suitable reagent for that. So here what we need to do is use a base so that this particular proton can be taken up and here you can generate minus. So if you can do that, that is nothing but your carbon. Uh, Here you have this. So negative set is generated now. This that's nothing but here base and the top this. So this is neutralized. So it is nothing but this carbon. Now if we look into the option, so it is a acidic medium would not be enough to do that. So that because base use correct. B would be some right option. Again, with ADMET, they want to know the correct statement. So, uh, for ADMET, exclusion of ethylene occurs during polymerization. Obviously, the small units are liberated with ethylene because that cross-metathesis. So, here we are. So, for ADMET, one of the examples that we are discussing into that example. Here we are discussing. So for this kind of cases, when let's say this thing happens, so this is the first activation step. Now you have this kind of uh, elimination will be uh, so, when you have this, so this would be happening so that metal center carbon is now generating the long chain is and where you are generating what ethylene image. So in that way, for this case, for this part, same thing would happen. And when it would react with units and do that polymerization, this small part would be you got transferred uh, from your system. So this is the correct statement regarding your AD So this is right. So monomer should be cyclic, obviously not because A means a cyclic cycle. So here and for every cases, so to maintain this property, your monomer should be a cyclic. So B is not true. This is a right of because diene a cyclic system, a cyclic diene metathesis. So C, right? And generation to catalyst can be used for obviously be used for ADME. So for alkyne catalyst, so for a statement they want to know. So this is the example of alkyne metathesis or alkyne metathesis polymerization, and you seen is by product. So if we just talk about that polymerization, there you can get the mechanism for this. So trying successfully and now let's look into so let's look into a general scheme. So let's say this is your alkyne, which is R1 and your methyl that also should be this kind of way. So they are hard and carry this kind of group. At first, the initiation would happen like this, uh, where you have kind of unit. First, this thing would happen to the group formation of these. Again, same thing. This bond is broken. So here we have simulated this unit and R1 bond. So there you can see that this particular bond is broken. And in that process, you have generated this kind of unit. So for this one, it is methyl one. So carbene that you are going to use, and this should be like this. So, 1, 2, 3. This 4 unit would be there, and that is nothing but your this this also used. So this part and this part. They need to be coupled to each other so that this particular triple bond is activated. So in that process, you are going to generate the right few time. So in that way, actually, your uh, alkyne metathesis work. So for that, carbene also should be this kind of unit should be there. So that this particular way it can happen and can break. these two bonds, which would ultimately lead to this for cross metathesis. The oxidation state this lithium synthesis, it is actually uh, so you can calculate this. We have carbene here also. uh, Now coming to metathesis, general overview. So in the metathesis section, what we are doing study for is that we are just swapping this particular thing. This if we consider it as A, so this is B, this unit is E, and this unit is D. So the metathesis you can to form this AC and BD. This is the general idea to for cross metathesis reaction, and with this kind of metal carbon units, actually they are able to do that. So that's the general idea for this kind of metathesis. So the mechanism we are already looking at it many times. Before that, this mechanism, there are some proposals regarding different kind of mechanism, and if we look into the different proposals for mechanism, we can explain that particular question. Mm, this initially, there are these kind of proposals, like are they pairwise or non-pairwise? So, one of the earlier proposals was the metal directly react with two units and have this kind of transition state. And then this CH2 unit, this happens, and here you have this CH2 part and this part. So that's how the pairwise manner the mechanism can occur. So this is a initial proposal, and uh, another proposal was this with five-member transition set, where you have this kind of thing, and you can only end up with this two moieties, where uh, what is better? So, okay. So these are the pairwise mechanism that is initially proposed, and this is the modern mechanism. So at first, one of the unit is executed like this, then followed by kind of thing would lead to formation of this particular isomer. So now, for confirming the right mechanism, so kind of units are taken. to prove that. To prove that, if you are with this option. So, if you have this and kind of unit, so when you do your pairwise mechanism, so then you would want so to do that pairwise mechanism, you initially form this unit kind of thing and with that carbon. So, it's going to be formed. So, cyclized product of that is going to be formed regardless of this thing. So, this is for now here you are forming one part. Now, for the second uh, this this thing, you are going to generate this page. Now, if this react, we are going to end up with this. It can be told, said that if it goes to kind of mechanism, formation of this unit should not be possible because this issue should not be there because they are ultimately converted to this one. So we are going to see formation of this or as it is go via this pairwise mechanism. So that's the reason only this part can also be. So that's how uh, is initially confirmed. And for this case again, you see all possible isomers are in that way. But if you if you go via your pairwise mechanism, obviously, then you can only see variations like so here remove feminist formation of these and this C3 H5 this one. So this kind of thing would be there. That's actually this non-pairwise mechanism have been used. So the mechanism of that, it must be got executed like this way, then the normal mechanism that we are following. Um, let's try this. Yeah, okay, now coming back to the discussion. Uh, in that way, we are doing and followed by this differentiation. We have seen for carbon and carbon. Uh, these are the graph catalysts. Uh, this is the first one. So initially, actually, that PPH3 that is when they are used. Now, after that, they are replaced with this kind of cyclohexane PCY and followed by this image. And then this is the second level. So in that way, it have been synthesized. So with this it is reacted with cyclopropene kind of ring opening leads to formation of this product, and that's the initial example of this kind of graph catalyst. And with this kind of azo compound, this is also can be, this can easily synthesized. Now we in heterocyclic carbons, uh, it potassium hydroxide as a first reached, uh, where your carbene is generated, and that actually reacted with this first, and you have your uh, sorry, this PCY that can be removed, and you have this kind of so that this is the variations that we are learning or we are seeing. So here is a summary of that. So for cross metathesis, you are uh, attaching these two units and these two parts. So that's how that cross metathesis is happening. Coding closing is very much easy. This one formation would lead to making a ring. That's why it is a ring closing. And for dyne metathesis, there this one formation does not happen. What it does is in this particular double bond system, they actually so no intramolecular intermolecular reaction. In, okay, that's right. This along this thing, and the chain growth we can see. Wording opening. This bond breakage happens. This so kind of this thing you can say. So that's why ring opening followed by polymerization. So ion metaphase is also there. So if you have in here and ion, this reaction would lead to formation of this ring closure and here double bond. So it's known as in metathesis reaction. For ring opening cross metathesis, for ring opening metathesis, metathesis, uh, at first this ring is opened and followed by this the smaller unit that is presented initially. So with ring opening, these two double bond should be there, and here is actually activated like this. So now along this way, this is uh, again one cross metathesis happens, and again with this two units, another cross metathesis happens. This is a combination of ring opening and cross metathesis reaction. So that's it, known as ROCM. So some of the examples of how they have been used in different synthesis. So if you have this unit, so to make that seven-member ring initially with swap carbon molybdenum one, this is used. So uh, for formation of this particular product. So how ring closing method is what will use this carbon, this, and ultimately we have this one, and then the ring closing. This is formation of. For this case, again the same way, here that ring closing could happen, and you would can make this 14 member ring that can be make this. uh, Again, again, here you can say again that for formation of this rings with huge ring system, they are actually this ring closing metaphys reaction with graphs. Sometimes for carbons are very much popular because for this kind of huge chain ring making, this is actually used. So this is another example of that, and this was used by Nicolau for synthesis of this particular molecule. So, for this one, this is the example of normal cross method to make this particular cross metathesis product. We have used this for cutting, and they have got up to this 92%. So this one we are seeing that ring opening metathesis followed by polymerization, but here polymerization is not happening. They able to stop it in this particular state, and due to they have used this particular additional monomer. So at first here this ring opening block her, so that would lead to formation of this product followed by the striding unit that is given and ultimately lead to photograph. So that's how they are able to control that. And then is a cross metathesis. So this part is crossed with this one. So this is actually example of that combination or cascade influencing reaction. So at first here this should be activated like this. Now here you can do one uh, metathesis reaction like this, and it is actually combination of ring closing and ring opening. So with first step you are doing a ring closing reaction, ruthenium, and here now the ring opening would be happening. So first is ring closing followed by ring opening. So you consider these two, A ring is closed and B is open. So if that this is generated, now second ring closing metaphys will happen and ultimately can lead this kind of image. So the schematic on for the real application, if you have this kind of scaffolds where this reading is there, so that can be okay, and this ring closing can be done, so you can end up with this uh ring closing product and open. So that's how this RCM, ROM, and RCM. So it is for E9. So that also can be done in the ruthenium catalyst and EYN E9 method can happen like this. So at first, the alkyne would be activated like this. This is that way it would lead to this product now. Is opening followed by this equalization and again regeneration of catalyst and this ring closing product will be option for the product that will be isolated. So that's how different metathesis reaction can be done, and you can end up with different required products according to your need. So that uh, 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 in that way you can conclude that metathesis part. So now, if you have any question, you can ask now, or today we can close. So next week, Tuesday would be that concluding class, I think, for 2 hours. So with that, we can conclude. So regarding today's class, if you have any question, you can ask now. So then in the next class, we would summarize that 8 lectures that we have done, and so, regarding today's class, if you have any question, you can ask now. So, seems like okay. So, thank you all for joining. So, I'll discuss, continue. We will continue our discussion in the next class. So, thank you. Thank you.